Swayam Prabha. Digital India. Educated India.
Good morning, students. So today we will do the last lap of the lectures on graph algorithms. So as discussed, we will talk about applications of DFS, and in specific we will talk about two applications. One is cycle detection and the second is topological sorting. So let's take up the first problem of cycle detection. So convince yourself that if a back edge is present while a DFS is run on a graph, there should exist a cycle in the graph. So this is easy to see. I'll leave the proof to you. This is very easy to see. Okay, if you just look at the the DFS tree structure, then it will become very apparent. So if you have, say, a back edge which is UV, okay, so then in the tree edges, through the tree edges, there should be a path from V to U, okay, already. That's why this edge could not be included, and this path is brought back to U through the back edge. So you can try to do a more formal proof, okay, where you do both sides. That is an if and only if proof. This is what I leave to you up to for as a home task. Okay, so if cycle then back edge, if back edge then cycle. So I have already told you this part. This explanation is straightforward coming from here. What is tricky is the other part. Can you come up with a concrete argument that this will be true? That if there is a cycle in the graph, there will be a back edge in the Bfs traversal. Now question is, if we assume or if we agree that presence of back edge actually ensures a presence of cycle, then how do we detect such cycles? So can we, question is, can we modify the vanilla DFS algorithm to detect cycles? Okay, this is the question. Now through this, I'll also show you, by writing this algorithm, I'll also show you that the DFS pseudocode that we wrote last day can be implemented just by using a stack. Okay, so this is one of the applications of stack that you have learned in your programming and data structure courses. So this stack is actually simulated in the previous day's lecture by the DFS visit function, because that was a recursive call, and as you might remember, that recursive calls are actually processed through a stack. So let us write the code for cycle detection. All vertices colored white. Create a stack S. Color V gray and push V onto S. While S is non-empty, pick at the top U of S. If U has a gray neighbor, then there is a cycle. Else, if U has a white neighbor, say W, color W gray and push it onto S, else color U black and pop S. As simple as that. So this is just a very easy stack implementation of the DFS algorithm, which is also able to tell you whether a cycle exists or not. Okay. So we will look at an example to ensure what we have written is correct. So it's very simple. So if U has a gray neighbor, okay, then we detect a cycle. Okay, immediately we can tell that there is a cycle in the graph. This is where we have actually discovered a back edge. Okay, let's see how it goes. Let us take a very small example. Let's say this is our initial graph. Okay, so as you can see in this graph, B, D, E forms a cycle. So initially the stack is empty. Now say we start processing from A. Again I will use the blue color to represent gray, since I do not have a gray color on my tablet. So now the first thing that you do is the stack has A. So let's say we start processing from A. Okay. Then from here, the next step would be So from A, we now go to B, and the state of the stack is AB. Okay. From here, the next step, say we jump to C, and the stack position is ABC. Next, now since C has no further explorations left, it becomes black and it is popped from the stack. Next, so now we have come back to B and again restarted our exploration. Okay, let's say we go to D. In fact, that is the only option left with us. So we explore D, and now the new stack position is like this. Okay. So next, from here, from D, we visit E, and the new stack condition is now the next step is crucial. I guess you have already guessed. Now see, at this point, what do you observe? You observe that E, when you are trying to start exploration from E, E has a gray neighbor, and that is B. Okay. So at any point in time, when something comes back to the stack, which is still not removed from the stack, okay, you see a cycle. Or in other words, you find out that there is a node whose gray neighbor is again found. Okay, there is a new node that you have encountered, and then you start exploring that new node. Okay, and you observe that there is already a gray neighbor of that node existing, like the neighbor B of E in this case. Since B is a gray neighbor of E, so we can safely conclude that there exists a cycle. So the next application we will look into is, as I said, topological sorting. This is again a very important application of the DFS algorithm. But before we discuss topological sorting, we have to get introduced to some important terms. The first term is a DAG. Okay, a DAG, full form directed acyclic graph, is a digraph where no path starts and ends at the same vertex, or in other words, there are no cycles. So a directed acyclic graph is a digraph which has no cycles. Source. A source is a node that has no incoming edges. That is, in degree of a source is 0. Sink. A sink is a node that has no outgoing edges. That is, out degree is 0. A DAG has at least one source and one sink node. So it should have at least one source and one sink node. Given all this, a topological sort of a DAG GVE is a linear ordering of all its vertices such that if G contains an edge say UV, then U appears before V in the ordering. Example, say we have something like this, then U appears before V and V appears before W in the linear ordering. Okay. So actually topological sort is very important in many different applications in computer sciences. Okay. So one simple example is that suppose you have to perform a set of tasks. Okay. And this has to be performed in linear order. So, and only one task can be performed at a time, and each task must be completed before the next task in the order begins. Okay. Now say a computer is performing such tasks. A microprocessor in the computer is actually performing this task. So then in that case, you have to have a linear ordering of the tasks, and this can be achieved by doing a topological sorting on the task dependencies. Okay. Now you can achieve topological sorting by a simple DFS algorithm, and this is how we do it. Perform DFS to compute the finishing times FV for each vertex V. As each vertex is finished, insert it to the front of a list. Return the, let's say, a linked list. Return the linked list of vertices. As simple as that. You perform DFS, compute the finishing times. As a vertex is finished, you insert it in the front of a linked list. Now the final linked list that is left is what you return. So we'll take a simple example and look at how the topological sort is obtained. Say we have a graph like this. We start at 0. Okay. Go to 2, let's say. Okay. Then from 2, go to 4, let's say. Then 4 finished. Okay. So we put 4 at the front of the list. Now go to 2 back. Now go to 3, 3 finished. Put 3 at the front. of the list. Now again go to 2, 2 finished, put 2 at the front of the list. Now go to 0, then from 0 go to 1. 1 has all neighbors that have been visited, so 1 finished. Put 1 at the front, go to 0, 0 finished. Put 0 at the front of the list, and in this way you get a topological sorting of the graph using a simple DFS algorithm. Now, as you understand that depending on how you visit, you can have multiple topological sortings of the graph. So it is non-unique in nature. So we have come to the last segment of our graph algorithms chapter. So here the last thing that we will talk about are the Bfs traversals. Okay, like DFS goes from one vertex to a deeper vertex and explores through the depth, BFS explores through the breadth of the graph. This explores the graph through the breadth. So specifically, you can think of it as a layer by layer discovery of the vertices. A layer by layer discovery of the vertices. Okay. A simple algorithm is as follows. Say if you want to do BFS starting from a node S, we take the following steps. Color is gray, insert S into Q. Like DFS uses stack, BFS uses a queue. While Q is not empty, do take vertex U of Q for each edge UV in E. Do if V is white, that is, in this case UV becomes a tree edge. Then color V gray, insert V into Q. Finally, color U black. So now you see that unlike DFS, where you are going depth by depth, here at one depth you explore all the neighbors of a particular node. Okay, you visit them and then you go to the next breath and then the next breath. So it is a layer by layer exploration. Let's take an example and try to understand this. Let's say we have a small graph like this. Okay, and let us say that we start from 1. So then we will put 2 and 4 in Q. Okay, and this could be in any order. Let's say we put first 4 and then 2. So then next we will process 4 since it's at the front of the queue, and we will put 3 in queue. Okay, then we will process 2 and then finally 3. So the layers that we will obtain are 1, 2, 4 and 3. Okay, and the 3 edges, as you can immediately understand, would be 1, 2, 1, 4 and 4, 3. As simple as that. So this is just a different way of seeing graph traversal. While DFS does it through a depth by depth exploration, BFS does it through a layer by layer exploration. One of the beautiful applications of BFS comes in the context of graph coloring. So we will first introduce ourselves to the concept of K coloring, and then we will see where the application lies. So the concept of coloring vertices is a very important application in graph theory. A K coloring is a partition of V into K sets such that each of the K sets are disjoint and no two vertices in the same set are adjacent to each other. A graph which has a k coloring but no k minus 1 coloring is called k colorable. Many key terms. Okay, first, k coloring. It is a partition of the set of vertices into k sets, okay, where each of the k sets are disjoint and no two vertices in the same set are adjacent to each other. Okay, and a graph which has a k coloring but no k minus 1 coloring is called k colorable. Let us take an example and understand this. Let us say we have a graph like this. So this is our very simple graph. Okay. So now let us try to color the nodes of the graph. Okay. So if I color this node as red, now this node, since it is adjacent to node A, since node B is adjacent to node A, I cannot use the red color again because we have seen that by definition the colors of adjacent nodes should be different. So then let us say we use the color blue for B. Now what happens for C? We can neither use color red nor can we use color blue because both A and B are adjacent to the node C. Therefore, we have to use a third color, say green. Okay, and we cannot color this particular graph with less than 3 colors. So this graph cannot be colored using less than 3 colors. Okay, so you need at least 3 colors to color this graph. Okay, so and note that this graph is nothing but an odd cycle. Okay, so this graph is also an example of an odd cycle. Now where does this kind of odd cycles matter? Let us take an anecdotal example. In the context of a special kind of social network or social graph, where our vertices, okay, are set of man, woman, okay, and age denotes a sexual contact. Now see, a very simple exercise tells us an important property of this graph. If we are not able to color this network using just two colors, okay, let's say for man we use the red color, and for woman we use the blue color. If we are not able to color this network using just the two colors, then this network has same sex relationships. Okay, so that means if there is an odd cycle in the graph, then if there is an odd cycle in the graph, then you can immediately conclude that there exists same-sex relationships in the graph. So you see that this coloring idea and these odd cycles have very important, could have very important applications. Now, in general, identifying the colorability of a graph is not so easy. However, for the case of a bipartite graph, this is not so difficult also. So this is a very special case. For bipartite graphs, it seems that the problem is not very difficult. So consider a non-null bipartite graph. Now the two partitions be denoted as V1 and V2. So in such bipartite graphs, V1 can have one color, say red, and V2 can have another color, say blue. So that means a bipartite graph is a two colorable graph. So now questioning whether a graph is two colorable amounts to questioning that whether the graph is bipartite, and this in turn amounts to questioning that whether the graph has an odd cycle or not. Now, as we have seen that if a graph has an odd cycle, if there is an odd cycle, then we will need at least three colors to color the graph, and therefore such a graph cannot be two colorable, and therefore cannot be a bipartite graph. This can be proved more formally. So the thing that we have to prove is G is bipartite if and only if it has no odd cycle. So how do we go about doing this? So there will be two directions. The direct one is as follows. Let us say G is equal to VE. E is a bipartite graph. So also let the two partitions be A and B such that is null and edges run from nodes in A to nodes in B only. Suppose G has at least, now this is a technique of contradiction that we will use to prove the theorem. Suppose G has at least one odd cycle. Let the length of the cycle be n, and let the cycle be represented as V1, V2, Vn, V1. So without any loss of generality, let us say V1 belongs to A. This would mean that V2 would belong to B, V3 would again belong to A, and so on and so forth. Okay. This can be generalized and written as for k in 1 to n, Vk belongs to A for k odd and belongs to B for k even. But as n is odd, so Vn should belong to A. And also we started with V1 already in A. Okay. Now, since Vn V1 is part of the cycle, therefore Vn V1 belongs to E. That is, there is an edge from Vn to V1. Otherwise, this cycle could not have been formed in the first place, which then contradicts with our assumption that G is bipartite. So this completes the direct side of the proof. Now the reverse. Let's assume that G has even cycles. Let V0 be any vertex. Now say for each vertex V in G, dV denote the length of the shortest path from V0 to V. Now color red every vertex of G whose shortest distance from V0 is even. Similarly, color the other vertices whose distance is odd from V0 with blue. Now note that if there is an edge between any pair of red nodes or any pair of blue nodes, then an odd cycle will be formed. This is because if you have the shortest path of even length, okay, all these are colored red, and if there is an edge between any pair of red nodes, then this will form an odd cycle. Similarly, if there is an edge between a pair of blue nodes, then also it will form an odd cycle. And this cannot happen because G only has even cycles. Thus, G must be bipartite and the blue and red nodes defines the two partitions. So this completes the proof. Now, once you have proved that a bipartite graph cannot have an odd cycle, you can use BFS to identify if odd cycles are present in a graph. So this is a very simple modification of the original BFS algorithm that we wrote. And this is a homework for you to try. Okay, try to convert the simple BFS algorithm into a one which will identify whether odd cycles are present in a graph, and if there are no odd cycles in the graph, then the graph is bipartite. So we will end this chapter here. There are lots and lots of interesting problems around these traversal algorithms, and we will share some of these with you in the tutorial classes, and also as supplementary materials. But if you go into the web, you can yourself also search for many such problems and solve them yourselves. Thank you very much.